Okay, I am going to share the screen for a minute and go to our Canvas page. And I'm in the student view, so you should see exactly what I'm seeing right now. Okay, all right, so I'm going into the module that was for Tuesday that just passed and this Thursday, and it's all about setting up problems. And I had a few questions. Students started going through the whole statics analysis because the problems I'm beginning to do are ones that you may have seen, at least the 2D ones in physics. But I only want you to do the setup. So that's why I wrote an announcement. I just want you to do the setup. So I'm just going to go over that. So steps in solving statics problems, right? Click on this and open link in a new tab. And here are the steps. But the setup, notice I have a line here. The setup only includes the given and the find, the table, and the free body diagram. Then there's another line, and then the rest of it is the solutions. And I want you to just be doing setup right now. I want to spend time setting up the problems in a good way, okay? So then I'm going back to the module, and these are the problems. This is the first problem we worked on. And today we're going to be working on these 3 problems. So there's another 2D problem, there's a 3D problem, and then another a little more complicated 2D problem, okay? And again, we're just doing the setup. So what I'm going to do now is use my document camera. So I'm going to stop sharing here. Getting rid of the background. Okay. Getting rid of this light. Not so good. Can you see it forward or backwards? Could you read it?
I can read
Yeah,
it.
it's fine.
Yeah, it's good.
So it's not backwards for you? No.
No.
Okay. All right. I don't know if I need to zoom in a little more. It is very cluttered right now, this page, so it looks very cluttered, but this is the problem that we worked on Tuesday, and I did scan it and post it. What we did is we took a look at the schematic, the sketch that was given. We read through the words to see if there was any information in here about the problem that wasn't communicated by the sketch. So we looked at the sketch, we read the problem, and we wrote our given. And our given first was all the stuff inside the sketch, because I'm not going to write all that stuff. So I just write sketch info. Then we learned in here that the cylinder was 500 pounds. And then what did we have to find? The problem asked us to find the tension and find the force exerted by the inclined plane, and we know that's the normal. So we're going to use standard variables for tension and normal, okay? We also saw that it's a homogeneous steel cylinder, which we knew that the material is the same throughout, which means the center of gravity is right in the center. We also learned that it's supported by a flexible cable, which means it could be pulled. A cable, if you could take a rope and pull it, but you can't push on a rope. A rope does not take compression, but if it was a bar, it could take tension and compression. And then we also learned that it was a smooth inclined plane, which meant there's no friction, and we're not going to see friction until whenever, far from now. So this was the given and find information, and then we made our table. The table is 3 columns, the force, the magnitude, and the direction, because each one of these forces is a vector. It has 2 different pieces of information. It has the magnitude and the direction. So one may be known and one unknown. And what we found was in this system here, there's a weight, there's a tension, and there's a normal. The weight magnitude is given. We do not know the tension, so we put a question mark. We do not know the normal, we put a question mark, but we know the direction of all three of them. So in the end, there are two unknowns. And when you have two unknowns, you need two equations to solve it. And for a 2D body, we know for 2D bodies, we know we have two equations, some of the forces in the X and some of the forces in the Y. So since it's a 2D body and I need two equations, I only need to analyze one body. Everybody got that? Right? It's a 2D problem. I have two equations. I needed two equations, so I only need one body to solve it. And we picked the point where all the forces converge, which makes all these forces concurrent, which means the only possible motion that I could have on the system is translational motion linear. But because it's a statics problem, we're going to prevent it. So I picked the dot, the particle, as my point I'm drawing a free body diagram of. I drew my tension, I drew my normal, and yes, you could draw your normal up here if you want. I drew my weight, put in the directions of all the forces, labeled all the forces with either values or variables, and put a positive X or Y axis. And that's where I stop. To set up, yeah?
I have a question about the table.
Yes.
So regarding the setup for some problems, let's say they don't give you the angle exactly, but they give you the ratio. Would you say that they gave you the direction, or?
Yes, because we've seen that some statics problems you have an angle and some statics problems you have a distance. Whether you're given the distance or the angle, you know the direction.
Okay, for sure. All right,
And
thank you.
you know, in physics, you probably saw angles, but think of a building, you know, or even a bicycle. On drawings, sometimes they don't put angles. You just know the distances. You know the lengths of the rods. You know the lengths of the house. You know the height of the house. Many times in engineering problems, you're not given angles, but you're given distances because that's what's more real to us. So you always have to determine, is this an angle problem or a ratio problem? This one is an angle problem because they give you angles, but angles give you direction. If they gave you distances, distances are giving you direction too. Thanks for the question, Angel. Okay.
I have a question too.
Yeah, Jason?
What if you had another tension? What would you call it?
You could call it T1 and T2,
Okay.
or you could call it TAB to TAC.
And you would label it as such on the drawing.
That's correct. On the free body diagram, you have to make sure that you're labeling all the forces with variables, and you use the same variables in your static analysis, which we're not doing right now. We're just doing
And that would
static.
correspond to the find and the force column in the table.
Correct.
And additionally, these
Okay, before you
T
go on,
and N.
Jason,
What's
hang
that?
on. So did everybody hear Jason? When you decide a variable, I decided T because there was only one. I put the T in the find, I put the T in the force, and I put the T in the free body diagram. I'm using the same variable. Because if you call this T and then this TA and then this TB, I think you have three unknowns. Always use the same variable in everything throughout. Great question, Jason. Next question.
Yeah, these are not categorical, as in this case, it could be mistaken for being categorical. Weight is different than tension is different than the normal force enough that you might think that these are categories rather than just the names of the variables.
Good point. So W stands for weight, so that's why I'm choosing it as the variable to represent the force, right? T, yes, represents categorically tension, but when you pick a variable is describing one of your forces. And the key thing of this whole thing is your free body diagram, right? When you come down to it, I'm not going to look at this stuff anymore, the table and everything. I'm just looking at my free body diagram, and it shows me that T is being used for this tension in this cable. And this normal is the variable used for this normal in this problem. Good. Okay, so let's go on to the next problem. Okay. Jordan, I'm going to start with you, okay? You know how I go around the room? No room, but, and you could say pass, you guys. So we're going to look at this picture, and let me move it up a little bit. And it probably needs to be upright for you guys. Great. Okay, first I look at the sketch. Okay, I have a block here called A. It's suspended on a rope. Notice, everybody look in close. Do you see number 2? It's a link, which means this is not the same rope. This rope here at B, this rope A and D are different. They're different ropes. They're all connected at 2. Does everybody see that? That's important to see, because if there was a pulley there and it was the same rope, it would have the same tension. And we haven't looked at those kind of problems yet. Same thing here. At point 1, there's a link. So A and C are not the same rope. And then there's an external load of 500 newtons here. So, you know, I think I'm just gonna write, again, this is scrap, because I like to write on the drawing that's given. That's TA, TD, TB, TC. Okay, now we're going to read the problem to see if there's any information given in the words that's not in the picture. Cable system shown as being used to lift body A. The cable system is in equilibrium at the cable position shown in the figure. When a 500 Newton force is applied at joint 1, determine the tension in A, B, C, D, and the mass of body A. Okay, so given. What's the first thing I want to write for given, Jordan? What did I write on the problem above?
The first thing you wrote on the problem above was the weight, and the given weight is the first given thing is the 500 Newton force at joint 1.
Okay. Okay, so I'm actually, what I write first is I always write sketch info.
Oh, yeah.
Okay, so let's write sketch info, because now everything in the sketch I don't have to write in the given, right? That 500 Newton force they told us about in the words is in the sketch, so I don't have to write it. I personally don't like to reread the problems a zillion times, so that's why I read it really thoroughly at the beginning and then write everything in the given, so that I don't have to go back to the words in the problem. So now, yeah, sketch info. Is there anything else, Jordan, that's given in the words that's not showed in the sketch? I think Jordan's frozen. Yeah. Okay, so we're going to Cody. Is Cody here?
Yeah. I
So
kind of need
Cody-
to analyze it a little more.
Okay. Well, let me just move on then. There's nothing else in here written that's not in the picture. So we're done with the given. Okay. So now let's do find. Cody, what do they want?
What about the fact that it's at equilibrium? Is that
Yeah,
something we should?
good point. All these problems, every single problem we do is going to be at equilibrium because it's statics. So yes, but no. When you get to dynamics, then maybe you want to write equilibrium, but every single problem we do in statics is in equilibrium. Sorry, we lost you, Jordan.
Wait a minute. I mean, the resultant
back.
problems weren't.
Right, well, yes, but I told you those were dynamic problems. Now we're doing only statics.
Okay.
Okay, all right. Okay, Cody, what do we have to find? What do they want us to find?
Was it tension in A?
Yeah, TA, TB, TC, TD, and they want us to find the mass of A.
I don't understand the little thing that says 10 degrees. What is that 10 degrees from? That's a really weird.
Oh, it's Probably because I
Drawing.
wrote the T over it.
Oh, that's what that is.
It's the degrees right in here.
It's like from the x-axis.
Yeah, it's from the
Okay.
negative x-axis to the C, the tension.
Gotcha.
Is it too small? Should I zoom in more?
It's just weird that it's written above mostly.
Well, in graphics,
I get that there's not space.
yeah, and Isaac, you didn't take graphics yet, so you don't, when you don't have enough space, you write it outside.
There is a lot of sort of guesswork here. Like, what does that dashed line represent?
It's parallel to A, right? And here's a dashed line. So what do you think it is? It's the x-axis.
That's probably
or the
vertical,
y-axis?
but is it, safe to assume?
So you could take a protractor out,
Oh, I
take
see.
a protractor and measure it.
They
Yeah,
show
okay.
an axis on the right there. There's a y and x-axis.
And
shown.
here's an x-axis. And what I love to use, but we use this in graphics sometimes. Here's this cool little thing. And
Yeah,
you put it
okay,
at
alright.
the x-axis and you go, oh, it's the x.
Yeah, that's some diligence. I'll take it.
All right, you gotta, yeah.
Yeah.
Okay. So now we have to find mass. Now, in statics, we only deal with forces. Is mass a force?
No.
No. So what's the force associated with mass?
Wait.
MG.
Wait, right? So mg. So really what we're trying to find is they want to know what the mass is, but in the end, what we really want to do is find out what the weight of A is. And we know that it's equal to the mass of A times G. Okay, so I'll put MA, well, let's see, are we using, what units are we using? Newton. So this would be 9.81 MA. Everybody good with that? And can you see it? Because sometimes static students think the mass is the weight and they solve for the weight, but they call it the mass and it's incorrect. You're finding weight. We are always dealing with force. Okay, so now I'm going to make my table. Force, magnitude, direction. We already said there's TA, TB, TC, TD, and the weight. Okay, Laura, we're up to you. Do we know the tension A?
No,
No. Do we know tension B?
no,
Do we know tension C?
no.
No. Okay, do we know the direction of TA, TB, and TC?
Yes.
Yes, we do. And the reason we do is we know that TA lies along the wire. We know TC lies along the wire. We know TB lies along the wire. The directions of the arrows for the tension depend on what I'm analyzing. Liam, is Liam here?
Yeah.
Okay, Liam, if I was analyzing point 1, what direction would I draw TC in? Towards 1 or away from 1? If I
Away
was
from
drawing,
one?
if I was drawing a free body diagram of point 1, my TC would be drawn away from point 1 because tension is always drawn away. How about Liam? How about for TA? Again, if I was analyzing point 1, how would I draw TA? Towards
Away
1 or
from
away?
point
Away.
1.
How about if I was analyzing point 2? How would I
Would-
draw TA?
Away from point 2.
Away from point 2. Everybody got it? Depending on the point, you're going to find, remember, this is all scrap. I could draw whatever the hell I want on here. Depending on what I'm drawing a free body diagram of, that's going to communicate the direction of my tension, because tension is always drawn away. Which way is normal drawn, Luis? How is a normal drawn?
Perpendicular.
Perpendicular to what?
To the surface.
Correct. And is it drawn towards the point? Is it drawn away from the surface or towards the surface?
Away from the surface.
Away from the surface. So we know, let's just shut this for a minute. So we know weight is always drawn down.
Yes.
We know tension is drawn along the cord away from the body you're analyzed because it's pulling. A compression force or a normal is always drawn, well, let's say normal is drawn perpendicular to the surface towards the body because it's a compression force. Okay?
Okay.
It's coming, hang on.
Joanne, do you want us to do that for like the initial sketch or
No.
for the full body? For
Yeah,
both of them?
you could do whatever you want on this, on the initial sketch. I mean, I like to draw on it, but you don't have to draw on it.
Okay, so you
Um,
want us to draw
but-
compression.
But you're, in the end, we have to draw the free body diagram. Yeah, I have
And
to-
you said compression is always drawn towards the particle.
right.
Okay.
Just like if, see, now I don't want that to be on. Hang on. Okay, remember the other day we put our hands together?
Yeah.
This hand is pushing on this hand. This hand is pushing on this hand. If I drew a free body diagram of this hand, I'd have to put the force going this way because it's a compression force. This hand is pushing in this direction. If I draw a free body diagram of this hand is pushing in this direction. It's a compression force. So we're going to take our first shortcut.
Oh, what's a
Uh,
body?
What? Yeah, hang on, it's coming. Lisa, you're an Mackenzie? Is Mackenzie here?
Yeah.
Okay, Mackenzie, looking at this picture, what is TD equal to?
TA plus TB.
Okay, well, it's equal to a component, the Y component of TB, but we're not doing that kind of math yet.
Okay.
Just look at this part. What is TD equal to?
Do you want me to give you the X and the Y components?
No, no, no. Look below. There's a block hanging from TD.
Okay, so the mass of A,
Not the mass, the weight.
the weight.
Right?
Okay. Mm-hmm.
So this right here, the weight here that's of this block is suspended through here. This cable is equal to the weight. Does everybody agree that if I took a free body diagram right here at point 3, you would have the weight going down and the tension going up, which means TD is equal to the weight of A. Does everybody agree?
Could you
Thumbs
repeat
up?
that one more time?
Okay, so if I have a rope and I have a weight suspended from a rope, that rope is experiencing the weight.
Yeah.
I shove a hole through an apple. I put a cable. I now am holding a rope with an apple at the end. The tension that is in that rope is the apple's weight,
Yeah.
right? So I don't need to put that TD is unknown. Let's just say it's equal to the weight of A. Anytime you have something suspended from a rope, it's going to be that rope, that tension in the rope is going to be equal to the weight. So even though I don't know weight A, I've already accounted for the weight down here because I don't know it. I'll talk about that again because I see or am thinking there's questions. Do we know, I'm up to Marcine now? Marcine?
I'm here.
Okay, do you know the direction of TD?
Yes.
Do you know the direction of the weight?
Yes.
So how many unknowns do you have total?
4, technically, yeah, just 4, because weight A.
4 unknowns. If you have 4 unknowns, how many equations do you need? Marcine still. If we have 4 unknowns, how many equations do we need to solve 4 unknowns?
You need 4 equations?
Yep. 4 equations,
Joanne?
right? In statics or in math, you've had 2 equations, 2 unknowns, right? And you could solve for the unknowns if you have 2 equations. If you have 3 unknowns, you need 3 equations. Okay, so we have 4 unknowns, we need 4 equations.
Joanne?
Yeah.
Would you want to include the 500 Newton force in the table?
Oh, yes, thank you. Hey, Angel is awake. Good job. 500 newtons, we know and we know. Thank you. Because we want to put all the forces in the table that are present in the problem. Thank you. We still only have 4 unknowns, right? Okay, I want to go back to the tension in D.
That's
Wait,
interesting.
can I just ask something?
Yeah.
We have 4 unknowns because we know that one of our unknowns equals the other one, right? Because
Correct.
there's really 5, but we know that one equals
That's
it.
right, and that's what I'm going back to right now. So let's say you wanted to say you don't know TD. Then how many equations do you need? If you put a question mark into TD and you didn't need it, how many equations would you need? 5 equations, right? What equation did I actually do over here? What equation did I use to say that TD was equal to WA? Huh? Maria. Ooh.
The sum of the forces on the math at the point right there,
The sum of the forces here, but were the forces in the X or the Y?
the y direction.
I did the sum of the forces in the Y, which had TD going up minus W equals 0, TD equals W. So what I did is I did that 5th equation, but I did it in my head. So I'm saying that you guys from physics already know that this cable is equal to this weight. There's no need for us to do that equation. We could do it in our head. We know that the load of this block is being transferred to this cable, and I know TD is equal to that weight of A. So I'm skipping doing this 5th equation. I don't want to come up and say I have 5 equations and then have to draw another free body diagram. David, I think you have a question.
Yeah, Joanne, would it be appropriate to set up the table? Let's see. So you have TD equals WA on one cell, like.
Sure, you could do this.
Okay, yeah, because that way it would line up, and you'd have one line where like this quantity that's the same.
Yep.
We don't know that one. Yeah,
Yep, you could do that if you want.
thanks.
Definitely. Okay, so now, four unknowns, we need 4 equations. For every 2D body, we are on Matthew. For every 2D body, what equations do I have, Matthew?
You have 2 equations.
Yep, and which one are they?
The sum of the forces in the x and sum of forces in the y.
Right. So for every 2D body, I have 2 equations. So Matthew, because I need 4 equations, how many bodies am I going to have to draw for free body diagrams of?
Just 2.
Yes, I need 2 bodies. Okay, questions?
I have a
don't
question.
Yeah, Matthew?
Could we solve for TB and TA just by doing a free body on that one point on the right side?
Which point? 2?
Yeah.
Yeah, we're going to draw a free body. Yeah. And that's our next step. We haven't finished, right? The setup includes writing the given and find, doing the table, and now drawing the 2 free body diagrams. Okay?
Okay.
Jason, did you have a question?
Yeah, maybe don't get the 2D sum of force X, sum of force Y thing.
Okay. So for every free body diagram we draw, we could do some of the forces in the X and we could do some of the forces in the Y, right? From physics.
Yeah.
So that means from every 2D body, every free body diagram I draw, I could get 2 equations. So the fact that I need to find 4 equations, I need to draw 2 free body diagrams.
Uh-huh. Is that an essential part, or are you kind of making a side note, or is that like an essential part of the setup process that you'd like us to do?
In order to find, okay, so from the table, I know there are 4 unknowns. For 4 unknowns, I need 4 equations.
Uh-huh.
And now I have to draw the next step is to draw free body diagrams. And I need to know how many free body diagrams I have to draw.
Uh-huh. And so
Because
you make
there
a
are 4
note.
equations, I need 2.
Yeah, that they each have 2.
Okay, so Myra, is Myra here?
I'm here.
Okay, we need 2 free body diagrams. What do you want to draw a free body diagram of?
Point 2.
Good, point 2.
And then
What else?
is it point 1 next
Yeah.
to, yeah.
Now, why did you choose point 1 and point 2? Which are correct?
Because that's where we can get the most information from.
Good. And another way of saying that is all these forces, TC, TA, and 500 all converge at point 1. TB, TA, and TD, or the weight, all converge at point 2. Right? And right now we're looking at concurrent forces. So I have 500 newtons here. I have TA here. And I have TC here. And it's up at 10 degrees. And at 2, I have the weight of A. I have TA. And I have TB. And TB is at an angle of 20. So here's my free body diagram 1. And here's my free body diagram 2. Miles, what's missing from the free body diagrams? Not sure if Miles is here. Okay, Peter.
Normal force.
Okay, so take a look. One, when we read the words and we looked at the pictures and we wrote the table, we didn't put a normal force in. Where do you think there's a normal force? Because nothing's touching anything.
Oh yeah, no, that's
right.
There wouldn't be a normal force because
Yeah, there's
all
no normal
tensions
force.
connecting.
Right, all the tensions are just the only loads in there. But I have something missing, a critical thing that's missing from the free body diagrams. I have all the forces labeled with the directions, but I have something missing. What is it?
Would you want to break up tension TB and tension TC into X and Y components?
I could break it up, but I'm not going to because I could just do the math later on. What about axes?
Oh,
Right,
yeah,
I
you
forgot to
put
draw
it-
the axes.
Okay.
So you could draw the axes on each one if you want. If you want, you could just draw it off the side. But you have to have an axis in there. And this is the setup. You looked at the sketch, you read the words, you wrote your given and find, you wrote your table of all the forces present, you figured out how many free body diagrams you needed to draw. In this problem, we determined that it was 2. We drew the free body diagrams, and we're done with the setup.
Joanne, what's
Yes.
the angle of TB from the vertical?
Say that again?
What is the angle of TB
Oh,
from the
it's 20,
vertical
20 degrees.
in free body diagram 2?
Yeah, it's 20 degrees
That's
here
20?
and it's 20, yeah.
Okay, for sure. Thank you.
Okay. All right,
Yeah.
David.
Yeah, just a clarify question.
Yeah.
So theoretically, we've done the setup, and then we know it's like we could just do algebra. You could just do algebra now and solve it, right? You would
Right,
plug-
so
okay.
my point for not doing complete statics problems is I want you first to be comfortable with setting up all the statics problems. So that's why we're doing 4 problems and we're just setting them up. We're not crunching out the numbers. The next steps, if we look at those, the whole steps, if we look at the whole steps, the next step is to start summing up the forces. Some of the forces in the X from the first free body diagram is equal to 0. Some of the forces in the Y from the first free body diagram is equal to 0. And then we're going to solve the problem. But there's an efficient way of solving problems too, but I don't want to do that yet. I only want to just crank on setting up a bunch of problems so you're comfortable. So homework 5 is setting up 2D problems. Homework 6 is setting up 3D problems, and you're not doing the statics analysis yet.
I got it. Yeah, so we're just getting ready to solve, and then it would be a lot of like cosines and whatnot to get the
Yep.
actual numbers. Okay.
Exactly.
Thanks.
Okay, but one thing I want to do is I want to do a little bit of practice on free body diagrams. So you have these 2 free body diagrams here. I want you to take a moment and I want you to draw, let's say we kept cable 1, 2 intact and we didn't cut it. And you drew a free body diagram of 1, 2. Draw me a free body diagram of 1, 2. We drew a free body diagram of point 1. We drew a free body diagram of point 2. I want you now to draw a free body diagram of that cable 1, 2 intact.
You want the cable to be the particle?
Yes. In fact, it's not a particle now, right? It's a rigid body.
That's right. Well.
But it's not really rigid because it's a cable. But it's a rigid body. It's not a particle.
Flexible body.
Luis?
I had a question,
Yeah.
kind of what Angel was saying.
Yeah.
The diagram, it's just a little confusing to see the 20%, like the 20 degrees.
On the outside.
Yeah, is it just the
Okay.
way
And
it-
that's why on the curriculum for this course, it actually suggests you have engineering 25 done first.
Oh, okay.
So I'll just show you this quickly. When you have 2 lines, so let's say we have this big angle. I know it's not 20 degrees, but let's just say it's 20 degrees. I could put the line, the dimension line, and the arrows and the number inside. But as this gets smaller, I could still put the 20 degrees, but when it gets really small, I can no longer put the dimension line and the arrows, and maybe I could just fit the number in here. Or if it gets really tiny, I have to put the 20 degrees outside. Does this make sense?
Yeah, yeah.
That this is ideal. This is kind of squishy. But when you get really narrow, you can't fit the stuff in. So the key is the arrows. The arrows here touch the line in question. The arrows here touch the line in question. The arrows here still touch the line in question. The arrows here touch the line in question.
Not drawn to scale.
Not drawn to scale.
Okay, thanks for clearing that up.
Okay? Okay, does everybody have this free body diagram drawn? So let's see who we are. We're up to Tim. Tim, where are you? Okay, Tony. Tony here?
Oh, sorry, I'm here, Joanne. I don't
Oh,
know.
okay, Tim.
Yeah.
Okay, so Tim, when you draw a free body diagram of 1, 2, what forces do I draw in here?
So on point 1, we have the 500 Newton force going down.
Great.
On point 2 going down, we have the weight of A.
Good.
And then we have tension of B going 20 degrees off the y-axis on point 2. And then we have the tension of C 80 degrees off the y-axis.
Right. Yeah, I'm just going to write this.
Yeah.
Okay. I'm noticing that you did not include TA. Why?
Because it's essentially it's in equilibrium between point 1 and I mean it does have tension, but it's not going to help us really.
Okay. So the word you want, the answer is it's internal to the system.
Okay.
Okay. It's an internal force. There is a TA here. Everybody look up here. And there is a TA here. But mathematically, they're equal and opposite, right? Mathematically, they cancel each other out. But really, the main thing is TA is an internal force here. TA is an internal force. Because this is still intact, that force is being experienced inside. Free body diagrams only show external forces. And why are these forces external? Look up here, please. I am cutting TC to draw this free body diagram. Because I cut it, I'm only seeing this part of it, and TC becomes external. Here, TB, I'm cutting the cable. I only see the TB coming out of 2. TB becomes external. This was given as an external pull, and weight is always external. Always external. Does everybody understand that?
Does this mean we can just disregard, can we just treat point 1 and 2 as 1 point?
You cannot treat it as 1 point. And the reason why, is everybody with me?
Mm-hmm.
At point 1, these are all concurrent forces. The only type of motion we're trying to prevent at point 1 is linear motion, right? Because they're all concurrent forces. Same thing at 2. 2 is only experiencing concurrent forces. We're preventing linear motion. But when we look at this body together with all these forces, this TC can spin point 2. It could cause a rotation. That's why there's a difference between the statics of particles and statics of a rigid body. We have to prevent the rotational motion here. In statics, did you ever use the equation sum of the torques equals 0?
In statics?
I'm sorry, in physics 4A.
Oh, in 4A, yeah.
Did you ever say sum of the torques equals 0?
Mm-hmm.
Okay. For concurrent forces, the only equations here are sum of the forces in the X and sum of the forces in the Y, because there's no potential of a rotation. But when we deal with rigid bodies, we are going to say sum of the torques are equals to 0. But in engineering, we call them moments.
So you drew this out just to illustrate the distinction between rigid bodies and particle physics.
Yeah, actually, yes, that's true. I did that too, but I really drew it to distinguish between what forces are external and what are internal to a system.
Gotcha.
Okay. Okay, so this is the end of my setup. I did the given and find. I did the table. I found out I had to draw 2 free body diagrams. I drew 2 free body diagrams. The setup is done. I did it. You stop there. Okay? Okay, now we're going to do another problem.
Does the word body encompass particles and rigid bodies?
Yes. For me, it
So,
does. I don't know
there's a
if,
catch-all.
yeah, for me, that would be a good question. Like, I'd have to look at the textbook and see, but yeah.
You know, I couldn't find it in that darn book. It's 300,000 pages thick, and I couldn't find body in the glossary, or I mean, in the index for that matter.
Maybe they don't say body. Maybe they just say particle, or did they say rigid body?
No, I
They
couldn't
did say
find it.
rigid body. All right, let's go on. Okay, so we're doing a 3D problem. Let's take a look at the picture. I have a block here, right? So there's going to be some weight. Let's just look really quickly. Does it tell you what the weight is? Read the words. I'm up to Victoria. Victoria, is Victoria here?
Yeah.
Okay, Victoria, do you see the weight of the block in the words?
Yeah, it's 500 newtons.
500 newtons. Okay, good. So Victoria, what is the tension in this cable right here?
500 newtons.
That's right. So the weight is, that's all we have there is the weight. Forget about that tension. All right, and then we have these cables. So let's look. A block is supported by a system of cables as shown in the picture. The weight of the block is 500 newtons. Determine the tension in cable A, B, or C. I'm up to Adam. So given, besides the sketch info, what was also given?
They also give us the lengths for, well, pretty much the X and Y components for the cables.
Okay, but besides, remember, when I write given, I wrote sketch info, so I don't have to write anything from this sketch over here at all, because I'm going to keep looking at the sketch. Is there anything, what was given in the words here that we didn't see in the picture?
Nothing else.
The weight.
Oh yeah, just the weight.
Right? I wound up writing it in here, but it was not given. Okay, and Adam, what do we need to find?
The tension in cables A,
Yeah.
cables B, and cable C.
Right. Okay, and I'm going to call them TA, B, and C.
Mhm.
Okay, table, force, magnitude, direction. So Amani, what are the forces that are present here?
We have the TA, TB, and TC. We have the weight.
Great.
Of the,
anything else?
And the tension in that, the one holding.
But we're never going to write this anymore. We're never
Okay.
going to write that tension. We're just going to say it's the weight and be done. Okay, so what about the magnitude? Do we have the magnitude of TA?
We can get it.
We can get it, but do we
No.
have it already?
No. No.
So it deserves a question mark. We need an equation. How about TB?
Nope, we were looking for it, and so for TC.
Right. What about the weight?
We have that.
We have it. Okay, Angel, what about the directions? Do we know the direction of TA? Angel?
My bad. I thought I was.
Yeah. No problem. Do you know the
We do.
We do. How about TB?
We do as well.
How about TC?
That we do.
How about weight?
Yes, we do.
Good. Bond. How many unknowns do we have in this problem?
We have 3.
How many equations do we need?
We also need 3.
Is this a 2D or a 3D body?
3D.
So how many equations, what equations do we have on a 3D body?
3.
Right, what are they?
X, Y, and Z.
And don't say X, Y, and Z. Say sum. I'm asking you about an equation. An equation has to have an equal sign in it. So sum of the forces in the X, sum of the forces in the Y, sum of the forces equal in the Z, all equals 0. Okay? So if we need 3 equations and we have a 3D body which has the potential of finding 3 equations, how many bodies do we need to analyze?
Just one.
One body. And what body do you want to analyze?
That center point.
Yep,
I don't
the
know.
link. That
Yeah.
link. And
Yeah.
why did you pick the link?
Because all of the forces are coming from it or touching it.
That's right. All the forces converge at this point. Okay? And bond, if I were to just draw scrap, if I were to draw the tension on here, and this is my body, which way would the tension be drawn?
Down.
Would it be drawn to the link or away from the link?
I'm away from the link.
Away from the link. So TA is like this. What about TB?
It would be pointed towards the B.
Right. And how about TC?
Towards the C.
Right. And why? Why are they drawn away from the link?
Because it's always, tension is always pointed away from the point that you're looking at.
Right, exactly. And the cable is pulling this link, right?
Yeah.
Okay, so the next step then, what's the next step? We did the given, Colin. We did the given, we did the find, we did the table. We figured out that we need to do a free body diagram of one body. What's the next step?
Draw the free body diagram.
Draw the free body diagram. And I'm going to spend a little time now. I'm going to do some erasing here because I know some of you are having difficulty in seeing things in 3D. And this week in lab, you're going to spend more time, but also you guys watched that 3D lesson video I had, but I was thinking of looking at this a little bit more. So well, just watch me for a little bit. I'm going to zoom in more. And those of you, it's the opposite direction of the way I would think I have to move. Okay, those of you who are in graphics have seen things like this, and it may be a little bit more helpful, more comfortable for you. So let's look at TC. Here's my TC. I'm looking at, I'm not going to draw the box yet. Okay, who are we with? We're with Daniel C. Is Daniel C here? Yeah. Daniel, on a 3D problem, everybody, always look at where the axes are. Okay, look at where the axes are. So if I'm going from, let's call this point A. No, we can't. If I'm let's call this D. If I'm going from D to C, and I'm looking at the direction in the X, Daniel C, what is the distance in the X?
Based off of the given numbers or just in general?
Off the given numbers.
The distance, wouldn't it be from the...
Give me the number.
Wouldn't it be 1.2 and
Correct.
1.8 on the...
Okay, good. So everybody watch me. Sometimes it's confusing. We know to get from D to C, we're going 1.8, 1.2, and 0.9. And we have to figure out which one of those are X or Y. Here is the X-axis. It means that the distance that's parallel to the X is the one that's the X distance. So Daniel, is 1.8, 1.2, or 0.9 parallel to the X-axis?
1.2 is parallel.
1.2.
Yeah.
So going from D to C in the X is 1.2. And is it positive or negative?
It would be negative.
Negative. So going from D to C in the X, it's negative 1.2. Okay, Daniel H. Daniel H here?
Yes.
Okay, Daniel, when we look at the Y-axis, what distance is parallel to the Y going from D to C?
1.8.
1.8. So what is the Y distance going from D to C?
That would be, yeah, it would just be positive 1.8, right?
Right, 1.8, and it's positive. Okay, Daniel I, what about the Z distance? Here's my Z axis. What's the distance parallel to the Z?
That would be 1.9 or 0.9, sorry.
Right, 0.9. And going from D to C, is it going in the positive or in the negative?
It's going to the positive
in the
zx.
positive. So I'm just going to write positive. You don't have to write positive. Okay, so hopefully that is helpful.
Oh, I
Honestly,
can't see what you're writing. Nope, other way. Eh.
good. So I hope that's helpful. One, you look at the axis and you find the distance parallel to that axis. Okay? Now what I'm going to do is I'm going to do what we would have done in graphics.
Could use your parallel ruler to help with those
Yeah, I
parallel
can.
lines.
But I'm going to do it without because not everybody has one. Okay, you guys, take a look at this. I had the 1.8 and the point went from here to here. So I drew a line that was parallel off of here. And then I also drew a line that was parallel off of here because 1.8, 1.8, 1.8. It's all going in the y direction. Then I drew a line parallel to the 0.9, 0.9, 0.9. This is 0.9. So where is D? Point D is at the origin. Point C is the upper right corner. Can you now see that in the X, going from D to C, it's 1.2, in the Y, it's 1.8, and the height is 0.9. So one way to do this is not even to draw the box and just look at the distances that are parallel to the axes that you're working on. That's one. Two, you could draw the box if you want. That might help. As you get along in this class, you're not going to have to draw boxes anymore. You're going to see it in 3D. And those of you who already took graphics may have an easier time than those who didn't. Those of you who have built a lot, like Tim, built a structure he's sitting in right now this summer, he could probably totally see this in 3D because he had to put all those windows in straight and put the roof in straight and the floors in straight. So he's already been looking at 3D all summer long. Luckily, it didn't burn down. That would have really sucked after spending all that time this summer building it.
Why would you say that before the end of fire season?
Yeah, hasn't yet.
I'm sorry. I don't think, all right, let's retract that, okay? All right, everybody get it? Let's do another one. Okay, you're gonna do it on your own now. Look at this TA. For TA, what's the distance in the X, Y, and Z? Do it. For TA, what is the X distance, what's the Y distance, and what's the Z distance? Don't call it out. Give everybody a little bit of time. For TA, what's the X, Y, and Z distance? Okay, so I look at the x-axis. I'm looking for the distance that's parallel to the x-axis. It's 1.2. Is it going in the positive or negative? So where am I? David L. Leopold. So going from D to A, Is it going in the positive or the negative x?
Yeah, it's positive 1.2 meters, positive x direction.
Great. Okay, David LR, Lopez Rodriguez, going from D to A in the Y. Here's the Y. What's the distance in the Y?
Negative 1.5 meters.
Right, it's 1.5 and it's going in the negative direction. And then Edgar, how about Z? What's the Z distance? Maybe Edgar's not here. Elizabeth?
It's positive 2.4.
Right, it's 2.4 and it's positive, great. And you don't have to write the positives, I'm just accentuating it right now. And again, if I wanted, I could draw my isometric. Oh. Okay, and then remember on that video, that 3D visualization video, do you remember another way that I suggested finding the distances? How about, remember coordinates? I don't know if you guys watched the video or not. You got to watch those videos. You know, I'm not an expert at making up multiple choice questions. So they may be easy. Watch the damn video though.
What's
Because
the question?
videos-
How do you find the distance from something?
Yeah, I'm trying to look at the distance. I'm looking at the X, Y, and Z distances.
Right.
Another
so-
thing, wait, I want to go back to the statement I was making. You might be able to do the quizzes without watching the videos because I'm not a good expert at making my multiple choice quizzes. But you have to watch those videos because the videos are important, okay? So the other thing is I did the coordinates. The coordinates of D are, it's the origin, 0, 0, 0. The coordinates of A, well, in the X, A, here's the x-axis, it's 1.2. And then in the Y, it's negative 1.5. And in the Z, it's positive 2.4. And then getting this distance here, I just do final minus initial. Okay, so that's 3 ways. The thing I find the easiest is make sure you look at the axes and find the distances that are parallel. Okay. Fourth problem. This is our last setup problem. Okay, let's look at the picture. Okay, so look at the picture. I have 2 cylinders. They're on inclined planes. The masses of the cylinders are 40 kilograms and 90. Determine the forces exerted on the cylinder by the inclined surface and the magnitude and direction of the forces exerted by the cylinder A on B when the cylinders are in equilibrium. Assume all surfaces are smooth. So again, we know we're dealing with friction. Okay, so what is given? The sketch info. But what else is given? I'm on Eric. Is Eric here?
Yeah, I'm here. The masses of the
Right. So I get the mass of A, it's 40 kilograms. And the mass of B is equal to 90 kilograms. I've seen enough people do statics problems where they forget to convert it to weight and just use the mass. So as soon as you write the mass, let's figure out what the weight is. The weight of A is equal to MA times G. And what value is that? I think I probably have it. 392.4 newtons. So as soon as you write on a statics problem, the mass, convert it to weight so you don't use the mass, so you do use the weight. So the weight of B is MB times G, and it turns out to be 882.9 newtons.
What's the coefficient you're using for G there?
98.9.81.
Okay, just checking. Thanks.
Yeah, because I don't think my calculator has G in it, so I think I probably just typed in 9.81. Okay. Okay, is anything else given? The masses? No. Okay, find. Gerardo, what are they asking us to find here? It says determine the forces exerted on the cylinders by the inclined surface. What's that?
The normal forces.
Right. The normal forces from the surface to the cylinder, right? And I have to draw it perpendicular, right? Let's put the weight in. I'm going to put the weight in. Weight of B. Weight of A. I have a normal and it's perpendicular. This is too thick. Let's try. I'm going to draw the normal and it's got to be drawn perpendicular. That's probably not so good. Let me get a pen. There's a normal drawn from this surface, and this is supposed to be a right angle. I drew it off a little bit because of that thick weight. And then here, there's a normal. So Gerardo, what do you want to call these normals? What variable?
A and B.
Good. So normal A and normal B. And now, Hyoji?
Yes.
You're here, right? Hyoji. Here, they're giving me an angle of 15 degrees that's from the horizontal to the surface. So where is this 15 degrees with the normal? It's between the normal and what?
X-axis?
No, try again. So take a look. The 15 degrees, I mentioned this the other day, the 15 degrees is between the surface and the x-axis, right? The horizontal.
Yes.
In geometry, this 15 degrees, two lines that are perpendicular to these two lines hold the 15 degrees. So if the normal is drawn perpendicular to the surface, what's perpendicular to the x, the horizontal, is the vertical. So this is where the 15 degrees is. Got it?
Yes.
Okay, so Hyoji, where is this 30 degrees? Where do I draw it for the normal?
From where it's a normal from?
From the normal to where?
Weight.
Right, to the y-axis, 30 degrees. Good. Okay, so determine the forces exerted on the cylinder by the inclined surface. So Gerardo said normal A, normal B. Okay, next is Isaac. Isaac, and determine the magnitude and the direction of the forces exerted by cylinder A on cylinder B when the cylinders are in equilibrium. So what other forces here do we want to find?
There would be a force between the two cylinders.
Right. So
Which
somewhere
would
in
be-
here, there is a force that the smaller cylinder is putting on the larger cylinder, and the larger cylinder is putting on the smaller cylinder. What do you want to call that? What variable do you want to give it?
Normal C.
A on B.
Okay, so let's not introduce C, but we could call it normal AB, right? Then you know it's between A and B, or just call it normal. Let's call it normal AB. So we also have to find normal AB. So let's just read it again. They gave us the weight. In the end, we were able to find the weights of the forces. They want us to find NA and NB, and they want us to find NAB. So, Jack, you here?
Yes.
Okay, Jack. If I was drawing a free body diagram of B, if I was drawing a free body diagram of B right here, which way would normal AB go? To the left or the right?
To the left?
Okay, let's try again.
To the right.
Okay, well, we're gonna talk about it. I'm looking at a free body. First of all, is a normal force a tension or a compression? Yeah. Everybody put their hands together. If you're pushing on a surface, is that tension or compression?
Compression.
Compression. Tension is drawn away, right? Compression is drawn towards. So if I look at body B, right now body A is leaning on body B, right? Is it causing compression or tension?
Compression.
Compression. So NAB would be drawn to the right on B. But how about on A? If I were drawing a free body diagram on A, Jason with an E, if I was drawing a free body diagram of A, how would A feel when B's leaning on it? Which way would I draw NAB?
That arrow would go to the left, and so
Correct.
you could draw it from the center point of A
Right,
going to the
right.
left. Yeah.
Okay. I also want to say, and this is going to be hard to see, so I'm going to draw it bigger. I'm going to assume that there's a theta angle here. And we're not going to go into reason why I'm doing that. I just want to move on from that. But this, quite possible, maybe the load is horizontal between the two. I would draw it up on AutoCAD. If it is horizontal, then theta is 0. But right now, I think it's at an angle. So we're just going to assume it's at an angle, not think about why. We'll talk about the why later. So right now, we have to find NA, NB, and NAB. And now we're going to make our table. Force, magnitude, direction. What forces are present? We have WA, WB, NA, NB, and NAB. We're up to Jason with an O. Jason Lee.
Hello.
Hey, Jason, I'm going to call you Jason Lee, okay?
Okay.
Your last name's quick. And then Jason, I'm going to just call you Jason.
Mm-hmm.
Okay. So Jason Lee, do we know the weights?
Yes, we do. It's
We don't have to, we know them. Do we know the direction?
yes.
Okay. Do we know the normal A?
No.
Do we know the direction?
Yes.
Okay. What is the direction? It's theta, right?
Right.
So
and it's
wait, no, I'm sorry. NA we know. I'm sorry, I jumped ahead. How about Jason Lee, how about NB? Do we know the magnitude?
no.
Do we know the direction?
Yes.
Okay. How about NAB? Do we know the magnitude?
No.
Do we know the direction?
Yes.
Well, do we know that angle or no?
To be honest, we don't.
We don't. We don't. So it's an unknown.
Okay.
Okay, so how many unknowns do we have?
4.
4 unknowns. How many equations do we need?
2. No.
We need 4 equations, but you're right. We need 2 bodies.
Right.
And what bodies would you draw a free body diagram of?
Draw it individually of 2 cylinders.
Great. So let's draw it on the other page so I have room. So here's A. Here's B. Weight of A. Weight of B. I have to turn my paper over. The normal of B. And it's at 15 degrees. We have the weight of A. We have the normal of A, and it was at 30 degrees. And now, take a minute. How do I draw my normal AB? And I need to make sure I put an axes in here. So I have to draw a normal AB on A and on B, and how do I draw them? I don't know if I need to go back to this for some of you.
Is it on B, you draw it towards A, and on A, you draw it towards B?
Right, so for A is experiencing a push, a compression. So it's going, and the way I drew it, it's going up. Some of you, I'm learning, like to just draw it on the other side, which is fine. But I'm gonna, and it's totally fine to do that, but I'm gonna keep drawing it this way just so that you know it is a compressive force. And this angle right here is theta. And this is NAB. So that means I have to draw it the other way, NAB, and here is theta.
Okay, lots of exaggeration on that now.
Yeah.
And so your convention with AB versus BA is that
Hang on a second. Wait, let people. So I have two free body diagrams, free body diagram A and free body diagram B. Okay, Jason, what did you ask?
your convention with labeling a force from and on to, I imagine. Oh no, they're both AB. What? Shouldn't it be B onto A and A onto B? Shouldn't they be reverse the letters? What's going on?
You could reverse the letters. Does everybody understand why he's asking that? Because this is force going from B to A, and this is force going from A to B. So Jason is suggesting that we call this NBA. We can do that. However, if we're using two variables, we need to specify that they are equal, because they're equal and opposite, right? Third law. So if you want to call one NAB and one NBA, it's totally fine. But if you give me a different variable, you have to say that they're equal. Because otherwise, when you introduce a new variable, it looks like it's an unknown.
It's similar to when we had a tension between 2 points, right? So when
Yes.
you had a tension between 2 points, it's the same tension, just it's pulling one way on one and pulling the other way on the other.
That's right, but it's not pulling, right?
This is a compression that is what, pushing on one from one direction and pushing on one from the other direction, but it's the same.
It's the
right?
same.
Okay.
It's exactly the same value. So the question is, you could just call them both by the same variable, or if you want to call them two different variables, somewhere you have to tell me that they're equal.
But it's not the same vector.
It's not the same vector, but the magnitude is the same.
Fine.
And the theta represents both. So now we have 2 minutes left. If I drew the two cylinders together, we're up to,
Joanne, could you show the free body diagram of B, please?
yes. Okay, wait. Okay. And notice I labeled the free body diagrams, right? Free body diagram A, free body diagram B, because later on I'm going to reference them, so you might as well label them. So now I have A here and I have B here. And Jordan, if I were to draw a free body diagram of these two cylinders together, what forces would I draw on them?
You would have to draw the normal force between them and both of their weights.
Okay, well, let's go back to that one. If B is pushing on A and A is pushing on B, and then I put them together, the force, that NAB force, becomes an internal force, and that's the only one I don't draw. Right?
So
it's
it's just
going
implied.
back to that tension problem, where when I had the 2 points separate, that TA was an external force because I cut the wire. But once I draw the two together down here, it becomes a rigid body, and now it's an internal force. Internal force. When I draw a free body diagram of these two things, I'm only drawing the external forces. So Jordan, what are the external forces that I would draw on this free body diagram?
The normal force for A and B and the weight for A and B.
Yep. And what else? What's missing? Cody, what do I have missing in this free body diagram? I drew the normals, I drew the weights, I drew the bodies, but what's missing? What do I need in a free body diagram?
Would it be the tensions? I'm gonna have to pass actually.
Okay, the axes.
Your axes.
The axes. So when I draw a free body diagram where the body is a point, this is statics of particles. Here, what kind of static is this problem? A rigid body.
Mm-hmm.
It looks like I still owe you the 10 minutes because I haven't given it back to you yet. Did Rob send you an announcement?
Yeah, there's a little video to watch before the lab.
Okay. So the problem he realizes that he actually moved a little too fast in statics. So we're going to have better communication in the future. Okay.
Fine.
You know, yeah. Questions, Jason?
Oh,
And I'm willing to stay as long as you want for questions, but those of you that need to leave now, you know, class ends at 10 to 11, you could leave.
Okay, thanks, Joanne.
Amani, you said there's an exam now, not in statics. Are you talking about another course or something? Yeah, okay, must be.
Oh, yeah, no, I was just responding to it as it kept up.
Okay, I don't have the chats open, so.
Oh, okay.
Sorry.
Yeah, no worries.
Okay. So remember, there's always a quiz in statics on Tuesday at the end of class, not at the beginning. And the problem, I'll send you an email. I mean, I'm sorry, I'll put in an announcement. It's either going to be resultant or setup. So I have to decide. I think probably setup. Okay, so I'm here as long as you need me. So whoever wants to stay and ask questions. Otherwise, I'll see you on Tuesday.
Thanks, Joanne.
Yeah, you're welcome.
Thank you.
Yeah, you're welcome.
Thank you, Joanne.
Yeah, you're welcome.
Hey, Joanne, I've got a quick question.
Yeah, Tim.
The force and free body diagram quiz, when that happens, are you able to unlock those like closer to after class? Like earlier in the day than 3?
I could, but what I'm trying to do, I'm trying to give a more limited amount of time. So it doesn't matter. So what is it, 3 to 9 or something?
Like
3 to
noon
10?
would be awesome. Or
Say it again?
like noon would be great, just a bit earlier in the day. I mean,
Okay.
it's not making or breaking it.
I want to only have it open a minimum, a certain amount of time.
Okay.
So if I open it earlier, I'm going to close it earlier. And I'm concerned with those people that have classes, you know, in the afternoon.
Mm-hmm.
What is it, 3 to 10? What's the opening time?
Yeah, 3 to 10.
3 to 10, so I give you 7
Can we
hours.
ask
I mean,
why
the
you
thing
only
is
want it
I,
open briefly?
you know, I need to make sure, well, I'm really just relying on all you guys not cheating, right?
True.
It's easy to, bless you, it's easy to do with online stuff. But I think you know how important statics is to your career. So you're not. But that's why I'm limiting the amount of time, and I'm trying to create a time that I think people would be available. So some people may only be available in the evenings. you know? So Tim, for you, explain, you want it open at 12.
Oh, I start my day pretty, I mean, 3 o'clock works. I start my day pretty early and then I'm done by like 5. That's like my window.
Oh, wow. So at 5 o'clock, you're not doing schoolwork in the evening? Okay.
No.
I think you might be, different than most people. How about the rest of you? Could you tell me is it 3 to 10 okay?
It works, yeah.
Yeah.
So the goal is to make it so that like we don't have a long window in which to potentially cheat.
Yeah, in essence.
Because you can put a time limit on the quiz itself, like once we open it, and then it can be done at any point, but once we open it, we're stuck to a certain time.
But you could redo it 3 times.
You can?
Doesn't it have a 15-minute limit?
I think it has a 15-minute limit already, Isaac. Has a 15-minute, you probably just finished the quizzes before the time limit. There's a 15-minute window, and then you could, I don't know.
I guess the issue is just if you have 3 tries, you have like the longer window you have to take it, the more help you could get from outside sources.
Right.
Yeah, I guess I'm just like the difference between like 7 hours and 12 hours, like 7 hours is so much time anyway. Like if I wanted to cheat, that wouldn't make any difference, I guess.
Right.
Yeah, I don't know.
But I think, Tim, you are unique. Does anybody else not do work after 5?
I'm on the same boat. All of my classes are in the beginning, and in the afternoon, I don't really have anything. Scholarly.
No. Tim's saying he doesn't do schoolwork after 5. You don't do work?
I try and always fail.
Yeah, same. Like, if I were to schedule it properly, I wouldn't be doing schoolwork in the afternoon. Like, I don't have any classes or anything after.
What about homework, Angel?
How does that work?
Yeah, Angel.
I mean, Tim and like Jordan and I start doing work like at like 8 a.m. usually. It's just Tim finishes his at 5 and I don't.
He's just, yeah. Well, you have a family, Tim.
Yeah, I have 2 young kids, so
Yeah, that's why he cuts it off at 5. Yeah.
I thought you meant like schedule-wise, like.
No. I'm
classes.
talking about homework.
Oh, okay, never mind.
So, Tim, you'll find it's going to change as you get older because the kids don't even want to be around you anymore. I'm just kidding. But what I find is from 3 o'clock to 7 o'clock is my time with the family because the kids get out of school and I'm with them. But you got all this online learning that's happening now. But basically 3 o'clock to like 8 is usually my window, or actually probably 3 to 10. And then at 10 is when I start working again. And then I'm up till 2 or 3. So we all have different times. Certainly, Tim, I see what you're saying. So yeah, I'll start it earlier, maybe at 1. But I don't know, is 1 to 8 okay with everybody?
It doesn't make a difference to me so long as I don't forget. It would, if I wanted to cheat, it would make like, it's such a huge time window that it would make no difference in the first place. So I just don't want to forget the quiz and accidentally not do it. Yeah.
Let me just make it 1 to 8, okay?
cool. Thanks, Joanne.
Yeah.
And I mean, I don't know,
remind me to take a quiz at 1
No, but
a.m.
if you want to have those 3 tries in, Tim, and I totally understand that. And if it starts at 3, you only have 2 hours for 3 tries.
Yeah.
I guess the key is to watch the video, watch the videos associated with the online quiz way before the quiz opens.
Yeah.
I think that would be your answer, Tim.
I mean, 3, like I said, I can totally make 3 o'clock work.
Yeah, Tim, I'm going to leave it as is. I'm going to leave it as is because I think that more people work at night than during the day. And just make sure that you watch the videos before so that from 3 to 5, you have 2 hours to do it 3 times.
Yeah, it's funny.
And we'll keep talking as it goes on because there's going to be online quizzes that might take longer and therefore you might need a bigger window. So we'll figure it out as we go, okay?
Okay, cool.
Okay.
Thank you.
Yeah.
Joanne?
What other questions you guys have?
I have a question about the convention of drawing compression versus tension forces.
Yeah.
Is that an important convention, like for like in our engineering careers? Like, is that going to be
It's
important?
important to know that tension is drawn away from a body because it's pulling a body. And it's important to know that compression and normal are pushing a body, so it's drawn towards the body. But you could pull it away on the other side of the body.
Yeah.
Right? But I think the convention, just to know that, okay, if this is my body and here's my cord, the force is going up towards the cord. Right?
Yeah.
But if it's leaning on a surface here, you have to know it's going, it's compression, it's not being pulled away, it's going towards, but you could draw it over here.
Okay. So it doesn't matter where we draw it, really.
Doesn't matter where you draw it.
Okay, for sure. I thought it'd be like important for like some career reason or something.
No.
Okay.
In fact,
As long as we know that
probably
up is up.
drawing it away, drawing a compression force or a normal force away is going to be a less source of error.
Okay. All right. Yeah, because that's how we've learned to do it for physics. So I was just
Draw it away. But
Okay.
just to realize it is a compression force.
Okay. Cool.
Yeah.
All right. Sounds good. Thank you.
Yeah. What other questions, you guys?
I have some concern about the NBA, NAB shuffle.
Yeah.
Because they really are different vectors. And wouldn't you agree that a force can be represented with a vector? And so if it's a different vector, it's a different force.
Correct. And if you want, but notice, I mean, I'm not very detailed about putting a line over a vector, but right now,
True.
right now, this is my force, right? And here it's magnitude, right? And here I know the direction of it. So here I don't know the direction, but yes, these two would be in opposite directions. The only thing I'm concerned about, Jason, is look at this for a minute.
Yeah.
If I put it on two lines and I write NAA, NAB here and NBA here and put another two arrows, somebody might think it's 6 unknowns. And I don't want that to happen. You're going to find, and I know, Jason, you and I saw a problem already where they called the tension AB, but it was really going from B to A.
Yeah.
So they're interchangeable.
Which is a little sticky.
Yeah, but.
Yeah, because I mean, if I want to take that vector and put it at, put the tail at my particle, yeah, it'll be going off in the wrong direction. Yeah, I
think it's more of, think of it as the what you know in your head. You know that these two forces are equal in magnitude and opposite in direction. And we're using the nomenclature of NAB and NBA.
Uh-huh.
Right?
Yeah,
so
I think
when we go ahead and write the equations for the free body diagrams, which we haven't done yet, once we do that, we're going to put it in the right direction.
Uh-huh. So if you were to, for example, for a tension, what would your convention be? Would it be force and then subscript 2 and then from, or from and then 2?
I always do it from and then 2.
From and then 2?
I think that's standard.
I don't know.
I
It's
think
reasonable.
In math, I think in calculus, it was always from and then 2.
From and then 2.
And
so a compression force is the opposite?
No, it's still from and then 2.
Okay, so the compression force, I'm particle A, the compression force from particle B would that force pushing on me?
Yeah, I see what you're saying. And I think that's where it gets, I see what you're saying because I drew NA. That's why when I have equal and opposite forces, I don't use two different variables.
Oh, that trips me out.
I just use one variable.
I want someone to be able to walk up to my paper and finish the problem for me.
Yeah, let me see. Let me just look in the statics book. Because I think that the statics books, at least the other ones, would always call them just one thing. Let's see. Didn't we look at a homework problem where they called it TAB, but it was really going from B to A?
Ha 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 ha. Let's see.
Pretty
What
sure we
would that
did.
be?
I think you and I looked at one
Okay.
before. The important thing is that it's in your head and you know it. I don't care whether you say TAB or TBC or T1 or T2.
Well, fuck, why write anything down?
You just make sure you're consistent with that variable. I know, you know, it's equal and opposite.
Mm.
You could call them T1 and T2. You know, call it N. You know, one is NA, one is NB, and call the other one N. Don't
Which
call
would
it
do,
NAB and NBA.
just call it
N.
Just call it N. And where would N be going?
Well, when you draw the free body diagram of A, it's going towards A, and when you draw the free body diagram of B, it's going towards B.
Okay.
I think, and the reason Jason, the reason why I kind of said to you guys, don't ask me any questions about that in class, is like you're analyzing it a lot, and I think it's really helpful and important, but I think at times it might confuse people because you're at a deeper level. People are still trying to figure out where to draw the normal.
Yeah.
You know, and if they're stuck at the normal, then talking about NAB and NBA just will really just. But I think the answer to that is we should have just called it N.
Yeah, could have done. Which implies that you have a bit more work to do once you get to that break off force diagram, that you have to sort of reestablish what that vector is, and it'll be different for the two.
I actually don't think it's more work. I think it's less work. Hang on. I'm putting on the thing again. Because here's the free body diagram. I would have just put N. I would have just pinned N. And in all the equations, the sum of the forces in the X and the Y for free body diagram A, the sum of the forces in X and Y for free body diagram B would have just had N in it. N, 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 N. Where now I'm putting NAB, NAB, NAA. Should I put NAB? Should I put BA? It just fucks it up.
Is someone going to walk up to the paper and confuse N to be the same force as N in the other diagram? It's not the same vector.
It's the same force, though.
It's
just
not
equal and
the same.
opposite. So in physics, would they call it N1 and N2? To me, it shouldn't have different variables because it makes it look like you have, if you have an N1 and an N2 or an NA, if you have an N1 and an N2, it looks like there are two unknowns, but there aren't two unknowns.
Yeah, but that's why we have a check column where we can say that we know that.
I don't know. You can do it the way you want. I know that you know. I think it just adds another variable.
All right.
Matthew, what were you going to say?
Oh, yeah. I just had a few questions.
Yeah.
I was working on homework 5, and this last problem, I'm going to see if I can show this on my screen.
Okay.
I don't know how well this is going to come out. I honestly don't know if you can see that or not. Can you see that?
Yeah, but we didn't do that. That problem isn't one of the homework problems.
What?
It was, it's 2.63a.
It
Did I get that right?
Yeah.
It is part of the homework that you signed.
Hang on.
Maybe I had the wrong picture up. I don't know.
Okay.
No.
But basically, my
Wait,
question
wait.
can be pretty simple. There's just a weight hanging down from a pulley, and then there's the cable comes around at an angle. Can I just say that weight?
Okay, hang on. I have to get to the problem. What is it? 2 point?
Okay.
6.3a.
2.63.
You know what page it's on? Okay, I got it.
Oh.
Okay, yeah. No, I'm sorry. I was looking at the wrong picture. I thought you were looking at the picture above. because we're going to do a problem.
yeah.
Anyway, okay, so 2.63. So we're only setting it up, right?
Yeah.
So, okay, so ask your question now.
Yeah. Can we say the tension from A to B is the same as the weight from C?
Yes, yes.
Okay.
And we haven't looked at that yet, and that's, sorry. I'll make an announcement about that. Yes, pulleys, whenever you have a continuous cable, the value is the same. Wow, I'm sorry that I didn't introduce that yet. So
Wait a minute. That could go
What?
astray.
No, this is what we did in physics 4A when there's no tension and pulleys.
What about the pulleys on the next page?
Those are going to be really fun. We're doing that next week.
Continuous line.
Yep, same
Careful.
tension. Same tension.
Pulleys move.
I also just had one other
They're
thing.
connected. Let's
Joanne.
hang on, Jason. Let me talk to Matthew. Okay, Matthew.
Yeah.
Okay.
Oh, yeah, just as I was tutoring online last semester, I had like an actual whiteboard that I was writing on, and I noticed that the left and right sides got flipped on the screen. So if it's helpful for you when you have your overhead, there's a way to kind of flip it back over so that you're not looking at a mirror.
Thanks, but I don't want to flip it if it's going to be backwards for you guys.
It won't. It won't. It only affects your view because it's
Oh,
normal.
really? I didn't know that.
Yeah.
Oh, okay, yeah. I know the mirror thing, but I thought what I see is what you see. So, okay. All right, well, great. Thank you for telling me that. So when I change the, flip the mirror, I'm only affecting what I see. Okay, great. Thanks for telling me.
Yeah. Do you want me to lead you through how to flip
No,
that?
I know how to do it.
Okay.
I just thought it flips it for you guys, so I didn't want to put it backwards for you when it's, yeah, okay, great. Thanks. All right, so I'm gonna send an announcement now that a continuous cable, maybe, yeah, okay. Amani.
Oh no, I had a similar question to what Matthew had, and
Good.
then it got cleared during class too. So I was just checking that my 4A info was on point or not.
So next week, so yeah, I picked a problem that I hadn't talked about. Next week, we're gonna look at problems where there are pulleys. So let me,
Okay, but then you set the precedent that whenever there's a continuous line, all it does is change the direction.
all right, hang on a second. The tension, does this make sense, you guys? The tension in cables that continue around the pulley are equal.
No.
Wait, why not?
Because what if you have to?
No, go.
But
How
it's
would
for the
I
whole-
how would I exclude a situation where I have another pulley and it moves? Your
doesn't
wording does not
matter.
exclude that situation.
It doesn't matter if it moves, Jason. It's still the same magnitude.
Well, Jason, I think what you're getting caught up on is if you have like multiple strings going back and forth between 2 points, what it does is when you pull on something and you actually lift a block, it changes the distance that you have to pull it. It doesn't change the, like for statics, it doesn't change how much you have to hold it. It changes how much, if you wanted to lift it, how much you have to, the distance you have to cover.
I can do that with a single pulley.
Yeah, well, if you have a single pulley, then let's say you have to pull it like 1 foot, but then if you have like 2 or 3 pulleys, now you're doing the same amount of lifting by going over 3 or 4 feet of distance by pulling it.
Yeah, I agree. But take a look at the problem she's showing on the leftmost. That's a single pulley. The line is continuous.
Okay, there's no friction in these problems. You ready?
Yeah. Yeah.
So this is T. The tension in this cable is T. What's the weight going to be?
Half of T. No,
Try it
twice
again.
T. Twice T.
Right. So the weight here is going to be 2T. And the reason why is if I did a free body diagram of the pulley, I have 2 T's going up and I have my weight coming down and I do sum of the forces in the Y and the weight is equal to 2T, which means let's think of it the other way. If the weight is weight, what value is T of the weight in this case?
1/2.
How much do you have to pull this to lift it?
It'd be like
What's the
half of W.
relationship? Right, half T is half of W. You want me to zoom in?
Thank you.
And same with the one next to it to the right.
No, we're gonna do them all. We're ahead of ourselves.
Oh, really? I'm sick.
Yeah.
I'm
Okay,
so
so
confused.
this is all about having to lift something really heavy that we really don't want to lift. So we're going to look at it in terms of W. This is W. If I set up a pulley system here, my tension is half the weight.
Yep.
Okay? Let's look at this. We're going to follow along. This is T. This is T.
Still
this is-
T.
This is T. They're all T's. What is T equal to?
Half the weight.
Amani? She just froze.
But I agree with Jason.
I'm lagging so bad.
Okay. But
So
are you,
sorry.
yeah, no
like
problem with
red.
that. But so we're doing, here we did a free body diagram of this point. And we had a T here and a T here. And we had a W here. T is going to be equal to W over 2. Do you agree, Amani?
Yes, I do.
And Tony, you're here too. Here, we have T, this is T, this is T. What is T equal to, Amani?
It's gonna be 1/3 of the weight, no?
Do the free body diagram.
Oh no, it's still gonna be 1/4.
Try again. Where am I gonna, I'm gonna draw, where do all the forces come together? They come together at this pulley. At this
Yes.
pulley, I have a T going up, I have a T going up, and I have a weight coming down. What is?
Oh, it's still 1/2.
Right.
Yeah.
Okay, so now don't anybody say anything out loud. Figure out what T is equal to here.
I need to.
That's a good one.
Can you see it?
Yeah.
Like going.
So in the first one, we drew a free body diagram of the pulley. In the second one, we draw a free body diagram of the pulley. And in the third one, we draw a free body diagram of the pulley. What is T equal to, Amani?
It's still gonna be 1/2.
Well, how many, when you draw a free body diagram, you can't. When you draw a free body diagram of that, you have a T here.
Yeah.
You have a T here. But you also have a T in the middle.
Yep.
So, oh,
Right?
okay.
So cool.
So
Oh my
T is
God.
equal to, Amani?
Hello?
What is T equal to, Amani, in this one?
I'm just trying to see that is this, oh, it's not hanging from up top. Okay.
When, Amani, when your computer, when your internet freezes, do you still hear me or no?
I hear like you're cut off, so I have to piece up the pieces.
Did you get a hotspot from Cabrillo yet?
No, I just felt selfish.
No. No.
Okay.
Jesus Christ, don't feel selfish. Take everything we give you. Don't fucking get a hotspot.
Because I have a Wi-Fi. It's just bad.
Doesn't matter. Amani.
Okay.
Think of it this way. You're not being selfish. You
Okay.
have to do your homework at school. I mean, you're supposed to be at school.
That's
And
true.
now you're at home. You know what? The college should be paying your Wi-Fi right now. Okay?
That's true, yeah.
So as soon as we get off this phone call, you got to go fill out that tech form and write down you want a hotspot before they run out.
Okay, I will do that. Thank
Okay.
you.
So the free body diagram of this pulley, okay, first, T here, T here. T here, T here, T here. T here, T here, T here. It's all a continuous cable. T, T. Now, when you draw a free body diagram of the pulley, you have the weight down and 2 T's going up. When you draw a free body diagram of pulley, you have a weight going down and 2 T's going up. When you draw a free body diagram of the pulley and you have a weight going down and 3 T's going up. So what is this T equal to?
I see what you're saying now about the magnitude being the same anywhere in a continuous cable. I'm on board with that now.
Yay.
Yeah.
Amani, what's T equal to here?
I'm not sure. Now it's tripping me out that I'm seeing it. It's coming from the bottom one to the.
Right. So that's all you do is you start where they have the label.
Okay.
Start at the label. Follow the cable. Is this the same cable?
Yes.
So it's T. Keep following it. Is it the same cable? Yes, it's T. And then when you draw a free body diagram and do sum of the forces in the Y equal 3T going up minus W equals 0 and T equals W over 3. I want you to look at it more again, okay?
Yeah, I'm just going to turn off my video, so maybe that would help.
Okay. Okay, so let's look at D now.
Yeah.
Here's T. T.
There's
T. T. What's
T.
the what's T equal?
How could that be different than the one before?
It's not. What they're
It's
trying to
gotta
tell
be T
you
over
is,
3.
people think, pulleys is one of those, what is it called? A lever, a pulley, what are those things called?
Simple machines.
Simple machines.
Yeah.
People think that pulleys are simple machines, and they are, but only if you connect them the right way.
That's right.
This fool connected it like this and thought he or she made it easier to pull it, but it's not. It's still
No.
what?
It's still,
It's
Still W over 3.
Yeah.
Yeah.
So even though the person went out, bought a more sophisticated pulley, hooked it up, it's still the same. This and this are the same, and this are the same. It's only if you connect them in a certain way that they become a simple machine. You could say,
Oh yeah, I guess
yeah,
what they bought themselves there is the ability to pull down instead of up, which is handy. Then you can use your own body weight to help you
Good
or
point.
something.
You could stand on the ground.
Yeah, yeah.
Good point. Yeah, the benefit of this is you could pull it on the ground.
Mm-hmm.
You don't have to stand on the ceiling. Good point. But it's not to decrease the weight, the
Yeah.
load. Okay, what about this one now?
All right.
This is a hard one, and don't call it out. T, 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 T. What is it? Amani, you want to do it?
Is it just going to be W in that case?
No. You got it, Okay, Matthew and Jason and Tony, what's T equal to?
1/4.
Yeah.
Wait, how?
Okay. So I'm writing all over my book.
I know, it's tripping me out.
I know I'm going to have to erase it all. Okay, so this one. Amani, this is T, right? What's this?
Another T.
What's this?
Another T.
What's this?
Another T. Oh, okay.
Boom.
So you have this thing. Can you see that? No.
It's a bit too zoomed in. Oh, here we go.
Well, let's zoom out now. You have this thing where the weight's down. You have a T here. You have a T here. And then you have a bar that has another T and another T.
Yeah.
You could say that the load in this bar is 2 T's.
Okay.
So this is sum of the forces in the Y equal 4T minus W. So W, the tension is equal to W over 4.
Joanne, I think it would help if we could see the diagram for the
Yes,
one.
yeah. Thanks, Tony.
Yeah.
How's that? Okay.
Yeah, that's good.
Thanks. And I know you're doing pulleys. We're going to look at we're not going to look at this. We're going to look at one continuous pulley problem next week. And then next week on Friday, you're going to be doing an activity in the lab on pulleys. So last week, the activity in lab was supposed to be 3D. And this week, it's now 3D.
So this is tripping me out. What if the what if the distance, huh?
I know where you're going. There's another pulley problem, but it involves some of the moments. It's where you have, and oh, I should write it down that I should get it from, hang on a second. I have this list of things I need to get from school. So I make one trip.
Also, Joanne, I don't know if you've noticed, but you've been recording this whole time, so you could actually just upload this whole tangent.
Oh, great. Thank you. Let me, I'm going to shut it off now, okay?
Okay.
Yeah, good point. I think